Welcome to our channel Tech LTE. So today we are going to discuss about the most important topic, that is RACH. We have already one video about the attach, so it's better that first of all you just go with the topic RACH, and I will share the link for the attach also. So it will complete your RACH and attach procedure both. So let's start today's topic, RACH procedure in LTE. So first of all, we need to understand what exactly RACH is, and along with that, there are a lot of points we're gonna discuss related to the RACH. First of all, what exactly RACH? So RACH basically stand for your random access channel procedure. Okay, and now the question come that why RACH is required. So already we have seen, like, whenever we have switch on the UV. Okay, so all the synchronization that has been done, PSS, SSS, MIB, SIB, all synchronization in DL direction we have, UV has already performed. So this is the first signal that is going to be synchronized in the uplink direction. So now we can justify the word that why RACH required. So going forward, we are having the other questions also, that why RACH, when RACH is going to happen, on what which particular occasion, then types of RACH, and going forward, we will see the other topics related to this, about preamble, preamble format, how this preamble is generated, when and where exactly we are going to transmit this RACH, uh, and this preamble. So a lot of question we will be having, and we'll go sequence by sequence. So the first thing, that why RACH required. Basically, there are two most important reasons that why exactly RACH is going to require. So you can see why RACH is required. So first thing is to achieve the uplink synchronization between the UV and the inode B. This is one of the important thing, that the UV must be synchronized in uplink direction. So for that one particular reason, and we need to obtain the you need to obtain the resources that you are going to send for the RRC connection request. So basically, for message 3, that is RRC connection request. So for this particular purpose, to obtain the resources for that, we are going to have the RACH procedure. So these are the two most important reason that why exactly we are going to have the RACH. Now the question we have already seen. So sorry, this was for the why exactly the RACH is required. Now the next thing, that when exactly this RACH procedure is going to be used, or when exactly it's going to occur, when exactly it will come into the picture. So already we are seeing that whenever we will make the UV on, so for the initial, you can say, acquisition or initial access purpose, we are going to have this RACH procedure, and we are going to perform the RACH at the time of handover. Okay, so we'll see the different type of RACH also. So for the handover, we are going to have the RACH procedure, that is contention free, CFRA. Here initial access, it will be contention based. We will understand what is contention free and contention based. Okay, so basically, if you'll see when the RACH is going to happen, RACH is going to uh, take place at the time of initial acquisition or initial access. At the time of handover, we are going to perform this RACH. At the time of radio link failure, so we are already having one video related to RLF. I will share that link also. So at the time of radio link failure, where you can see the case of RRC connection re-establishment will come into the picture. So at that particular time, RACH is going to be, so to recover from that. Okay, so RACH is going to be performed. So these are the important areas, these are the important aspect where exactly the RACH is going to happen. Now the question comes that, okay, what are the type of RACH? So when we talk about the type of RACH, so basically it is defined into contention based RACH procedure and contention free RACH procedure. Contention free or non-contention based RACH procedure, you can call it. So what exactly the word contention itself? See, try to understand the word contention. Contention word means already it's a kind of tension, or it's a kind of argumented thing in between two or multiple entities. Okay, so if it is contention based RACH procedure, so definitely let's suppose this is our E node B. So definitely multiple UVs are trying to perform the RACH. Okay, trying to do the uplink synchronization. Okay, so for that particular purpose, so here there is an argument, or there is always a class while sending the preamble, while sending the message one. Okay, so that's the reason we are considering this as a contention based, where there is always argumented. Let's suppose multiple UVs are trying at the same time, not all the UVs are going to get the access for that. Okay, so now the question comes that, okay, that is contention based, then what exactly the contention free? Okay, and when exactly you are going to have the contention free? Contention based REST procedure at the time of initial acquisition or access, we can go with this contention based, because if it is not in one attempt, it is not, if it is not going to send the preamble, it will try for the second attempt. There is no any issue for that. Okay, and when exactly we are going to have the contention free? So if we are talking about the contention free at the time of handover, which is already our UV is attached and it is doing the handover, at that time we can't play with this kind of situation that, okay, multiple UVs are going to have that particular argumented thing, and where already one UV is already attached and going to perform the handover, and the two UV is going to fight. Okay, so here among the preambles, so there are 64 preambles. Okay, so dedicated preambles are provided by the enode B and for the handover purpose. So at that particular time, UV don't need to bother about bother about, or there is no any such kind of fight or contention between the multiple UVs. So there is already a dedicated preamble. It will pick and it will try to perform the handover. So this is one of the, you can say, the major difference that is in between the CBRA and CFRA. And whenever we are talking about the RACH procedure, so in last slide, we will be going through the SIP2 related parameters. So SIP2 basically contains importantly RACH related parameters. So we will see there are multiple RACH related parameters where your preamble information will be there, where how many number of array preambles it has selected for among the 64. Power ramping parameters are there. Preamble initial target receive initial receive target power is there. Preamble trans max, array response window size, max hark message 3 retransmission. So a lot of uh, information elements are there, which is in SIP2, where basically we'll focusing about PRACH configuration also. Okay, in that PRACH configuration, we will be having important Is like root sequence index, PRACH configuration index, high speed flag. All the that particular Is we will go through one by one. So now we are able to understand that what is RACH, why RACH required, when RACH is required, how many types of RACH procedures are there. So these are the points that we have covered. Now, one of the important thing that we are discussing about preambles. So we are discussing that okay, there are 64 preambles, okay, which is going to be used in the LT. So first of all, try to understand that what exactly you understand by the preamble. Okay, so this is one of the important question that comes in mind, that what exactly preamble means. So preamble you can consider a unique signature also. Okay, that there are 64 unique signature which your UV is gonna pick and try to send to the inode B as a message one. Okay, or you can say this, it will start synchronizing in the uplink direction by choosing that preamble. Okay, so if you, we can go with that particular example also. So first of all, try to understand there are 64 preambles being used as per the 3GPP in the LT. Okay, so preamble is a kind of signature, or if I'll take one example, let's suppose there is a door, or somebody has given a party, okay, and there is a door, okay, and he defined 64 kind of knocking pattern. Okay, and he invited, let's suppose, 200 300 people, and he already designated that okay, there are 64 pattern which has been defined. So whoever will be coming, use any of the 64 knocking pattern. Let's suppose single knocking, double knocking, three times knocking, two times knocking, then wait, and then two times. Likewise, 64 knocking patterns. Let's suppose somebody has defined or entering into the party. Okay, the people are coming. That you can call it as person one, person two, person three, or you can consider it as a UV1, UV2, UV3. All are coming and knocking. Let's suppose it has chosen double knock. It has chosen triple knock. It has chosen same double knock also, because there are 64 it has defined. Okay, so who, multiple people can use the same knocking pattern also, because that is valid, which is defined by the organizer. This is what exactly, there are 64 preambles in a LT which can be used by the UV. So UV can pick any of the preamble and it can send message one. Okay, that we will discuss later. So this is what in general preamble definition is. And what exactly preamble look like? What exactly the structure of the preamble? So you can see preamble consists of CP, that is cyclic prefix, plus sequence. So if I am telling about cyclic prefix, so the cyclic prefix, the understanding of the cyclic prefix and why exactly it is going to be used. Cyclic prefix basically going to be used to mitigate the intersymbol interference. This is one of the major reason that we are using the cyclic prefix along with the sequence. So this is the structure of one preamble. So you can see the length can be designated at TCP and T sequence. TCP is the length for the CP and T sequence is the sequence length. So if you will add this, it is one preamble. TCP plus T sequence is the length of one preamble. Okay, now the question come in this particular context, that what exactly you have, or what exactly the significance of T, this capital T S. You can see here it is dot TS, that we will discuss. So first of all, the length of the cyclic prefix plus T sequence will gonna give you preamble length. So let's see, there are four type of preamble format in FDD. Okay, and preamble format 4 is for TDD. So you can see preamble format 0, preamble format 1, preamble format 2, preamble format 3 and 4. So CP, we have already mentioned cyclic prefix, okay, which can act like a guard interval to prevent ISI, okay, intersymbol interference. And then we are having the preamble sequence. So preamble sequence, we can call it as a key component for the RACH message, okay. So what you can say, it is specifically designed sequence used for the UV identification and for the timing alignment, this particular sequence, okay. And there is one more term that is going to be used, we will see in the calculation, guard time. And why exactly guard time always added at the end of the preamble, okay. There are multiple preambles at the end of the preamble so that it should not overlap, okay, between, let's suppose multiple transmission is happening from the different UVs, so it should not overlap, there should not be confusion. That's the reason we are adding a guard time, okay. So there are, I have already mentioned that, you can see here there are four preamble format: 0, 1, 2 and 3, and based on that the length will change. So you can see for preamble format 0, what exactly the TCP length, 3168.ts, okay, and T sequence length 24576.ts. So this is, if you will add it, it will give you one complete preamble length when you are going to use a preamble format 0. One more important, you can say, aspect will come into the picture, that why exactly we are going with preamble format 0 generally in our regular deployment model. Okay, there we are having multiple, then why exactly requirement of multiple preamble format? So that answer we can get it from this particular calculation. Okay, and try to understand what exactly TS is. So TS generally refers your, what you can say, the basic time unit. Okay, so basic time unit, if you'll go with uh, formula, I'm not going much more depth, but if you go with formula, it will be uh, this particular seconds. Okay, so you can call it, it is the smallest time unit which is going to be used in the LT. Okay, and if we go a little bit more, so that, yeah, is basically derived from the sampling rate. And what exactly the sampling rate we are taking to derive this, that is 30.72 megahertz. This is the sampling rate if you are going to use in 20 megahertz of the system bandwidth. So this is what exactly the smallest unit of time being used, that is 1 by this much of second. Now if we are going to calculate, if we are going to use the preamble format 0, so what should be the radius of from where exactly UV can pick the preamble and can send? Okay, so this is what exactly preamble format is going to define. So the maximum radius we will calculate, so you can see the preamble format 0, it is having the TCP length 3168. If you're going to convert from this TS, that is the smallest unit in ms, in millisecond, you are going to get 0.103 millisecond. Likewise, if you convert this t sequence into millisecond, it will be 0.80. So the total length, like TCP plus t sequence is your length of that preamble. So it is coming around 0.903. That is nothing which will be approx we can consider as a 1, or 1 in a standard we can consider 1 millisecond. If you consider in a frame subframe, so it will be 1 subframe. Okay, and the guard time that we are going to have 0.097, so that it should not, while doing the transmission, it should not interfere with the other. And while calculating the radius, so it will come around 14 kilometer. From 14 kilometer maximum the UV can pick and can send the preamble. So that is reasonable. Okay, that is the maximum. So we are in LT, we are having the E node Bs at the distance of 1 kilometer, 1.5, 500 meter. So maximum, let's suppose if the other E node Bs are not there or it will down, so UV can pick preamble maximum from the 14 kilometer. Okay, and see, if you go with the other preamble format, it is 75 kilometer, 28, 1 which is practically in normal scenario, it's not required that your UV should peak the preamble from 75 kilometers or 28 kilometers. Then why exactly these preamble formats are being used? It is being used in such area, like suppose in huge forest or in a mountain area where there is a huge interference. There basically we are going to use this preamble format to mitigate the interference in that particular area. And let's suppose the E node B distance is too much high and too much more, okay, then we are going to use for. But in general scenario, generally we are going with the format 0. So this is what exactly about the preamble format and what exactly the preamble is. Going to the next topic, that we understood what exactly preamble is. Okay, now the question come that fine, we have understood that there are 64 preambles and the preamble format. Now the question come that okay, when and where exactly we are going to send this, or we are going to transmit this RACH. Okay, so as per this 3GPP table, this is from one of the 3GPP table, to understand about when and where exactly you are going to send your PRACH. Okay, so now try to understand in a very simple manner, like the E node B, okay, reserves a specific resource block also for PRACH. Okay, so there are two important configuration that from the SIP2. I will show you that what are the IEs that we are going to use. So one of the IE that we are going to select is a PRACH configuration index. Okay, and one more important parameter, that is PRACH frequency offset. So we will understand about these two things, which will give you the answer about when and where exactly does a UV transmit the RACH. Okay, so there are 64 PRACH configuration index which has been defined as per 3GPP. You can see from 0 to 63, and we will take one example to understand that how exactly you can read this. Okay, let's suppose if it is configured with PRACH configuration index 2. So if your inode is configured with PRACH config index 2, it means that your UV gonna use a preamble format 0, and it can select for sending that preamble, okay, to transmit that RACH any system frame number. So whenever we are telling about system frame number, there are 1024 system frame number. So it can choose even one. Okay, like it can go with 2, 4, 6, 8, and so on. Okay, so we know that PRACH config index 2 preamble format 0 it's gonna choose. It will choose a system frame number any even one, and let's suppose it has chosen 6. In that 6, let's suppose, so it is like it is only the radio frame number SFN. Okay, in that particular radio frame, 7th subframe, let's suppose 0, 1, 2, 3, 4, 5, 6, 7th. So 7th subframe is going to use for the transmission of that particular preamble. Okay, that particular RACH exactly the where exactly you are going to transmit. So this is particular location. Okay, so this is what exactly PRACH configuration index significance. If you take this one preamble form PRACH config index 5, it means it is going to use 0 preamble format. It can go with any SFN from 1024 and go with 7 subframe number. Okay, this is how exactly you want to read this. Now there's other important I that PRACH frequency offset. So PRACH, one of the important thing that is PRACH frequency offset. So PRACH frequency offset basically it will give the location in the frequency domain. And let's suppose if we take the example 5 or let's take the example 7. So what exactly that means? It is telling that the transmission occupy the resource block from 7. Okay, it is going to start from RB number 7 and it will go till the number where exactly your 6 PRB gonna complete, like 7, 8, 9, 10, 11, 12. Okay, so likewise it is going to go up to that particular number where 6 PRB is going to be covered. So this will be giving you the starting point of the RB number from where exactly it is going to be counted. Okay, now it's very important to understand that, okay, we understood there are 64 PRACH preamble. Okay, now the question comes that how exactly that 64 PRACH preamble generated, and this is very, what you can say, very important aspect to understand. And I have already mentioned you about, so there if you are talking about, there's one of the important thing that we need to discuss is root sequence index. PRACH config index we have already discussed, and PRACH frequency offset already discussed. We are going to discuss about root sequence index, high speed flag, and zero correlation zone, which is going to help in generating 64 PRACH preamble sequence. Okay, and I will go with the technical definition, and I will take the example also that how exactly we can define this three definitions. Okay, so if we're talking about the root sequence index, okay, so you can see the root sequence index, so here it is 100. I will take the example and try to understand the significance also, but try to understand what exactly root sequence index is telling us and what is the definitions. If we'll go with the definition, root sequence index indicates that which specific ZF2 sequence the cell uses the first. Okay, so for RACH procedure, okay, so we are having 839 ZF2 sequence. From 839, 64 preamble is going to be generated. Okay, so what exactly your root sequence index is giving? Root sequence index is telling that which specific ZF2 sequence the cell going to use first. So you can say the starting point. Okay, and the mobile device then create as many as cyclic shift from that particular sequence. Okay, to generate the 64 preamble. Now we will try to understand. I will take one example also to let you understand about this. Try to understand what is zero correlation zone role in this. So what zero correlation zone is, you can say, one of the setting that is going to control that how many cyclic shift a mobile is going to, or your UE is going to create from one ZF2 sequence. Okay, so if you gonna check, if you're gonna take one of the example, or to understand what exactly this means. So root sequence index, you can consider the base sequence. Okay, or if you take an example also, like root sequence index is nothing but your alphabet. There are 26 alphabets. Okay, so it is like alphabet, and all preambles, 64 preamble that we are talking are, that are words. The 64 preamble is nothing but these are the words which are generated or made from these particular alphabets. Now the question comes how. So, or you can say the root sequence index, what exactly it is giving, the starting point. Let's suppose if I'm taking the 100 we have said, so it is going to tell this is the starting point from where exactly you are going to generate the sequence. Okay, and if you are talking about the zero correlation zone config, okay, so zero correlation zone, it's going to define the cyclic shift between the multiple sequences. I have told you that this is the starting point from where exactly multiple sequence is going to be generated, and how that sequence is going to be generated. So the root sequence basically divided into small chunks. Okay, that we call it as a cyclic shift. Small with the small shift, it is going to generate the unique sequence. Okay, so each cyclic shift or chunk that we are talking about, okay, that creates a different version of sequence, multiple sequence. Okay, so what exactly zero correlation zone config is giving you? Zero correlation zone config defines the cyclic shift between the sequence. Okay, or you can say the step size. Okay, let's suppose this is one sequence generated, so the second sequence generated after this particular step size. This is what exactly your zero correlation zone config. In a very simple manner, you can understand in. Okay, now what is high speed flag? So high speed flag gonna give you the understanding. Let's suppose if your UV is moving slow or fast, so that it can identify between the cyclic shift. Okay, so whenever it is going to be slow, then we need to choose different zero correlation zone config set, that cyclic shift NCS. We'll discuss on that. Okay, so if we are going with the slow moving object, okay, then we need to go with unrestricted set. If you are going with the fast moving, then we need to go with the, I will go with the calculation. Let me first of all understand this. I believe that this particular part is clear to you, that how exactly it is going to be, what exactly the significance of this. And now we will understand with the example. So here root sequence index is 100. It means this particular is the starting point from where exactly it will start doing the cyclic shift, and it will keep doing the cyclic shift till your 64 preamble generated. Okay, and what exactly the cyclic shift, what you can say, the duration or the size, step size, that is nothing but your zero correlation zone config. Okay, now try to understand that with the example, that how exactly it is mapped, sorry, how exactly it is mapped, or how exactly we are going to define the root sequence. So this is the 3GPP table. Okay, so this 3GPP table has put that physical root sequence that is denoted by mu. Okay, this, that is, these are the values 839 ZF2 sequence. So they are they are put based on the 3GPP. They are put it in a small bucket, you can say, which is defined by the 3GPP, so that it will be easy for the configuration purpose and to be understood by the UV or the system very easily. So logical root sequence we have given as per the 3GPP. It has given like 0 to 23. We are going to use this physical root sequence. Within this bag we are going to use this. So likewise bag has been defined. So if I am going to take the example with above, so what was the example, what was the root sequence index? That is 100. If the root sequence is 100, what is the value of mu then? So you will see the bag. So it is coming under this bag. Okay, you can see this is 90, 91, 92, 93, 94, 95, 96, 98, 99, 100. So 636 is your mu value. That is the physical root sequence. And that is going to be used by the system further for the, in calculation. So we are having this mu value as a 636 because we are having the root sequence. Hence this particular sequence will be used as a starting point to derive that 64 preamble. Now what is the value of zero correlation zone config? 12. So if you will gonna see this zero correlation zone config 12. And what is high speed flag? High speed flag value is false. False is basically used for slow moving UV. And let's suppose that E node B is near the railway track or highway. There high speed flag settings we need to make it as a true, so that the slow moving UVs, means fast moving UV and slow moving UV will not get confused. So if the value is false, it means that it is a slow moving UV. Okay, so for that particular purpose it is going to use NCS as this one, the false one. Okay, if it is true, then it is going to use 158. So 119, what exactly it is telling? 119 is telling that this NCL, that is a cyclic interval. Okay, it is telling now you can get 64 different periods sequence. Okay, considering this as a base sequence, which you need to, base sequence we have already got it. Okay, the base sequence, and we will do the cyclic shift to get the first sequence, the second sequence, as by doing the cyclic shift of the base sequence by 1 into 119 samples. Likewise, the third sequence, fourth sequence till 31, we are going to be get it by this particular calculation. By 119 sample, which we got it from here, it will keep doing the cyclic shift and keep generating that 64 preamble. So this is how exactly your preamble is generated. Now the question come that, okay, we have understood about one more fundamental, that the period signal structure. Okay, and why exactly 6 PRB is going to required. So for this particular, you can understand, for the general radio frame, if you are going, the one subframe is of 15 kilohertz, and in 6 PRBs, if you are going to check, so 12 subcarriers are there in 1 PRB. Each subcarrier is of 15 kilohertz. If you are going with the 6 PRBs, then 72 subcarriers, and it is going to utilize 1.08 megahertz. Likewise, for the PRACH, one subcarrier is considered as 1.25 kilohertz, and as we are having 839 ZW sequence, so 839 subcarriers gonna use for that. And if you will go with the proper calculation to understand this, so preamble is, I've already told that preamble is made up of 839 ZW sequence. So if you are talking about the one preamble, so one preamble 839 ZW sequence. So if we are telling, and what is exactly the subcarrier spacing, or we can call it as the frequency, 1.25 kilohertz. So total occupied frequency, if we're gonna calculate, it will come around 839 into 1.25 kilohertz, which will be nearly about 1.048 megahertz, and which we call it as near about standard, if you'll go 1.4 megahertz. So 1.4 megahertz will, as per the spec, so it is going to occupy 6 PRB as per the table, 1.4 megahertz. That's the reason we are considering that for PRACH to be sent, they are going to occupy 6 PRBs. Okay, and if we are going to see how many in a time domain, so T is 1 by F on, you can see 1 by 1.25 kilohertz, that is F. So it will be nearly 0.8 millisecond, which we can so consider 1 millisecond. So this is what exactly in time and frequency domain it is going to be calculated. Now we have understood, till now we are understanding about that what exactly RACH is, why RACH, when exactly RACH is going to perform, type of RACH, what is the preamble format, and what is preamble, and then we are going to see when and where exactly you are going to transmit that RACH, then how exactly that 64 preamble got generated. So this is we have understood. Now when we are talking about the RACH procedure, the first message that is going to be sent, so from here basically your complete procedure is going to start for the RACH. So what exactly, whenever you will be going to perform the RACH, so message 1 that is going to be sent by the UV, or in a very simple manner you can call it like UV will send the PRACH preamble, correct? or RACH preamble. It will select, okay, that will be carrying RARNTI, okay, and that RARNTI will be decoded by the your E node B. So this is the first message, or we can call it a message 1, which is going to be sent from the UV side, UV to E node B. Now we have heard about the term RARNTI. So RARNTI, what exactly it is saying? The RARNTI is associated with the PRACH, okay, in which the RACH preamble is transmitted. Okay, that is what exactly RARNTI is. So if you go with the formula RARNTI, that is 1 plus TID plus 10 into FID. So generally FID for FDD, it is going to be 0. So if it is 0, then 1 plus TID, it is for the TDD. Okay. So, and what exactly the value for the TID? If you are talking about the TID range is from 0 to, in between 0 to 10. Okay, in a time domain, in a within the subframe. And if we are talking about FID, it will be from 0 to 6, that in a frequency domain. This is how exactly your RARNTI. So let's suppose if it will be 0, okay, then 1 plus TID will be your RARNTI. So message 1, if you are going to, if you have already sent the preamble and it is decoded by, received by the E node B, then E node B is going to send the response, that we call it as a random access response in message 2. So what exactly E node B is doing? E node B sends a RACH response with the RARNTI, which it has already calculated from the preamble, okay, and along with this message 2, a lot of information it is going to send, okay, like frequency allocation, and it is going to give the information about RB assignment, MCS configuration, and it is going to inform about that RRC connection request to UV for the message 3. So an uplink grant, okay, all this is going to be sent by message 2 along with TCRNTI. Once it sends a message to UV, gonna send message 3, and that we call it as RRC connection request. And at that particular time, your timer T300 is going to start. So this is your RRC connection request message, which is going to be sent by UV to the E node B. And what exactly it consists of? It will be consisting of UV identity, random value, because we can't use the MC directly, so that's the random value we are going to use, and establishment cause. Why exactly you are sending the RRC connection request message 3? Why? So it can be MOS signaling, it can be emergency, anything, okay, defined by the 3GPP. So this is what exactly your message 3 is. Whenever we are talking about message 4, so based on that, your E node B is going to send RRC connection setup message, and here exactly contention resolution done. What exactly contention resolution? Let's suppose two UVs are trying, A and B, both pick the same preamble and send it, okay, possibilities are there, and it is decoded by the E node B. Both get the same RAR, random access response, because E node B is not able to identify between them. And let's suppose that both send RRC connection request at the same time. So E node B get confused and it will accept that, and to distinguish between them, okay, that which exactly gonna get the RRC connection set up, because here already a lot of argument is there in between the two UV. That contention will resolve at message 4 based on the TA which is calculated at message 2 by the E node B. So that's the reason message 4 is the message where exactly contention resolved, and one of the E node B will get that, one of the UV will get that successful, and which is not going to get successful, they will again send the RRC connection request. This is how exactly it happened. Once RRC connection setup message sent, then E node B is going to send, U is going to send RRC connection setup complete message along with NAS, or we can call it attached request plus ESM or PDN connectivity request. This is your message 5. Also, whenever we are talking about the message 5, in message 5 there are few important things that we must need to consider. That RRC connection setup, what exactly it will be having. It will be having the details of PLMN identity, then what is registered MME, and that dedicated NAS info, that basically having the attached request and all. So, and what exactly registered MME that we are talking about? It will be consisting of PLMN ID, MME group ID, MME code. So this complete information finally it is going to send, you is going to send in message 5 to the E node B, and then it will go further for the authentication process and encryption. That video is already there with us, so I will share the link on that. And see, we will discuss 1 or 2 minutes on this, that there are SIP2 parameters, that is nothing but the RACH related parameters. You can see number of RA preambles. So there are 64 preambles, which is from among that 64, how many preambles are going to be chosen for this contention free, contention based. Okay, let's suppose in 64, let's suppose 40 it has selected, then 24 will be reserved by the E node B for the dedicated one. So this is going to give you the number of RA preambles. Okay, and you can see the information about, let's suppose U is trying to send and not able to send that particular message 1 from particular signal strength, then we are going to use the power ramping parameter, where it is ramped by either 0 dB, 2 dB, 4 dB, 6 dB. So generally 2 dB deployment is done, like it will ramp it by 2 dB or 3 dB, 4 dB. Okay, let's suppose -108 is your signal strength, so I'm not able to send that preamble, then it will ramp it by 2 dB. Okay, improved one, again it is not going to send, improve it by 2 dB. Okay, so it is improving. So now the question comes that how much time. So preamble transmax. Okay, so you can configure, let's suppose generally 10 or 8 people used to configure, like after 8 transmission again it will restart the transmission freshly. Okay, then RA response window size, it is basically in the milliseconds. Okay, so like when it is going to response RAR, that window size is like 10 millisecond, 8 millisecond, within that it should send the response. MAC contention resolution timer. Okay, that should happen within this particular frame window. Okay, and further we are having the PRACH configuration. So PRACH configuration, you can see the root sequence index we have already discussed, PRACH configuration index, high split flag, zero correlation zone, PRACH frequency offset. This all we have discussed. So refer the above video to understand the complete RACH procedure, and hope you must have understood this RACH. If any doubt, please do comment. We will be happy to assist you on that. So thanks everyone for watching this complete video. Please go through our YouTube channel, go through our LinkedIn page, go through our website. You can join our Telegram for the further information of any technique, and please do also comment that which particular next video you want us to proceed with. Thank you. Thanks everyone.